Today in this video, we're going to be discussing how waves add together and how that works with our sine waves and cosine wave equations. Watch this carefully here. There's, of course, this man here, I believe it's called boogie boarding, and right there, he goes for a little bit of a ride. And what in the world just happened there? All of a sudden, he's just going along, and boom, those waves just shoot him into the air. I have to admit, I enjoy watching this little GIF here. So what did happen? Well, we've got two waves that actually came together right there. If you pay attention, I'll keep going here. We've got the water coming back. Okay, so we had the last round of waves came up the shore, and it's going back out. And that wave ended up combining with the wave that was coming in, the one he was riding on. And of course, the result was, in this case, a little spectacular. They're not usually that spectacular, but this one definitely was. So that's what we're going to be looking at today, is how does that work? So let's just look at a couple of real basic sine wave equations here. I've got this one here. Think of this as y. Y is equal to sine of 2x, and y is equal to 1/2 sine x. And what would happen if I add them together? That's the question. So I got these two waves. Think of these as water waves or light waves or sound waves, some sort of waves that they're going along, and there's another wave and they're running into another wave. What's going to actually happen? And at first it's going to be a little tough to see this here as far as what happens. Here's the result. So I've got sine of 2x added to 1/2 sine of x. I add them together, and I get this kind of a strange result here. It doesn't even really look like a sine wave. If, you got a high spot and you sort of got this little weird deal going on there. It almost looks like some sort of polynomial graph or something. It's a really strange result as far as what in the world just happened there. So let me explain this by showing you a particular spot. If you notice right here, check out the amplitude of the red one, the y is equal to 1/2 sine x. It's right in that area, it's about 1. And the black one at the same point in time. Now remember, the x-axis always represents time when we talk about sine waves. At the same point in time, this one had a value of pretty close to -1. Well, the combination of them has an amplitude there of 0, or really close to it. And the result here, how did we get that? They're simply just added together. That's all that's going on. You're adding the amplitudes together to get the resulting wave. When two waves add together, that's what happens. So take this here. We should be able to sort of figure out what's going to happen. I've got this blue one here. It's got a b of 2. Okay, so it's going twice as fast as the black one here. If I was to add them together, what would you expect? Well, like right here they both have an amplitude of 0, so I would expect the new one to also have an amplitude of 0 there. Let's go over here. Well, same kind of thing there is happening. Up here, well, the black one has a amplitude of, I don't know, about 3/4, maybe a little more. The blue one kind of the same. If I add them, well, it actually should get taller. 3/4 and 3/4 is like 1/2. So it should get taller there. In this area here, boy, that's a little bit below 1, and this is a little bit above -1. They might actually cancel out to give you a 0 in that area. So let's take a look at it. That's pretty much what we were just saying right there. Almost up to 1 positive, almost down to -1. And when we add them together, we should get pretty close to 0. There's that 0 we were talking about there. There's that 0 we were talking about there. Here they were added together to give even taller than what it was. Here's an interesting spot here. One's again positive, one's negative, and again, the one they added together actually gives you nothing. They cancel each other out right there. So the red, of course, is going to be the result of adding those two waves together. Let's take a look at these two. Sine and cosine, they're out of phase by 90 degrees, or pi over 2 is what they are. Sine, of course, always starts at this average, and then goes up to its most, down to the average, down to the least, and back to the average. Cosine starts at its most, to the average, to the least, to the average, and back to the most. Well, what should happen here? Let's see. If we add the amplitudes here, we got 0 plus 1. Oh, that should give us 1. So the new one should be like right there if I add them together. Here, well, let's see. Again, we got like 3/4 and 3/4 to be 1.5. So it should end up there someplace. Here we're probably somewhere in this area. You know, we've got positive, we got negative. That's going to kind of cancel out. We might even get a 0 in there somewhere. Here we got 2 that are both negative. They should add and get something even more negative when we get there. You can sort of start to visualize what you're going to get. And there it is. And this one actually looks like a sine wave or a cosine wave. It doesn't look like some of those other ones that almost were mimics of some sort of polynomial thing. Here we had 0 plus 1 is 1. Here we had, there's a 0 and a negative 1, which gave us a negative 1. Like we said, we had 2 negatives here. They had to give you a more negative. 2 positives here had to give you more positive. And so it is really looking like what we would expect it to look like if you just simply add the amplitudes together. So when you're going to add waves together, you go to any point in time. Remember, the x-axis represents points of time. You go to any point in time, and you find the height of the one, you find the height of the other one, and you add them together. That's all that happens with wave addition. So you get some kind of weird things. This one here, why don't you pause this, and you think through what you think it should turn out like, and then go ahead and play it after you think you figured it out. All right, so there's that one. Notice here that with these, the high point of the blue was also the high point of the black, which is also the high point of the new wave, the one that got added together. 0 and 0, the low point. Okay, so we got the low points, and they're perfectly lined up. The high points are perfectly lined up. The low points are perfectly lined up. This is actually kind of a special situation here. Hopefully you got it figured out on your own, but this is a special situation. This we refer to as completely constructive wave interference. So when waves add together, it's got a fancy title. It's called wave interference. And you get these mosts of each one adding together to give you the most for the combination of them. And so they're completely added together. There's no canceling out at all. It wasn't like one of these is a little bit negative or one's a little bit more positive, or the other one's a little bit negative. All of this one's amplitude goes to all of that, and same down here. The wave is complete. There's no subtraction involved. And that is, I believe, what we were seeing at the beginning with that poor guy out in the ocean there, where those two waves just happen to line up perfectly to give a constructive wave, possibly a complete constructive wave interference. The probability of that's actually, I don't think it's very high. I think it's a pretty low probability of that occurring. For two random waves to just randomly happen to hit their peaks at the same time as they're getting added together. But it sure makes for something to smile about when you watch it. Of course, you've got to feel sorry for that poor dude. Hopefully he didn't get hurt. So that's a special case of adding waves together. Completely constructive, little vocabulary there, completely constructive wave interference. When their amplitudes line up perfectly to add the maximums and the minimums. Of course, the opposite of that would be if the maximums and minimums were the exact opposite of each other. And that's going to be something we're going to look at in just a minute. But before we get there, I want to talk about this constructive, and in this case, no pun intended, it's not going to look real constructive. But when waves add together, an example of that, of this bridge here, the Tacoma Bridge, or the Tacoma Narrows Bridge out in Washington. This bridge was built back in I believe it was 40, and it didn't last very long. And you just watch this here.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
All right, so the Tacoma Bridge. I like the part at the end where the only casualties were a car and a dog. And you'd think they'd maybe have said the dog first. But yeah, everyone had cleared off. The bridge didn't last very long. Only, if I recall, only a couple of months after the time it was completed until it fell apart. And it had to do with wave additions, the resonating bounce of that particular structure and the addition of that with the waves of wind coming through there set that off. Well, let's look at the other thing we discussed, which I said it would be what's called destructive. Now, in this case, what that means is they cancel each other out. So constructive, they add together to give you something even bigger. Destructive, there are two waves that cancel each other out. And you can see it's going to happen here with this one. We've got 0, 0, well, that's still going to be 0. Here we got up to 1, down to -1. Well, of course, yeah, then that's going to be 0 right there. Again, 0. And so if you add them together, the exact opposite wave, and here the negative sign really shows its true meaning. The negative means the opposite of. One wave added to its opposite wave, they give you a canceled out. And you could call it a wave, but it's really nothing. There's just really nothing there is what there is there. So this is referred to as completely destructive wave interference. With most things in life, you're not going to get completely constructive. You're not going to get completely destructive, typically unless they're designed to be that way. You get some sort of combination in between when you're listening to music and you've got voices and you've got instruments and there may be some background noise, and all of those things are adding together and going into your ear. You're hearing combinations, all kinds of different kinds of combinations in those senses. Most things are only constructive, completely constructive or destructive by design. Airplane wings, because they tend to wobble as they go through the air, similar to the Tacoma Bridge, they are designed so that the wobbling counteracts by going the exact opposite direction in one part as the other in relation to the vibration from the wind to cancel out, and what they sometimes call dampen, to dampen the harmonics of the wave. So there's a lot of things that are engineered to be constructive or destructive. So back to the airplane wing, it doesn't really do anything, which is the way it's designed. It just sits there, it doesn't wobble. If it did wobble, they'd get to flapping like a bird's wing and they'd break off in midair and it'd all be really bad. But they're designed to have this completely destructive when you add the amplitudes together. Here's another thing that's by design. If you've ever seen the earmuffs used, a lot of times like shooting guns, where the noise canceling headphones, what they do is they take a sound that comes in. Okay, so a loud sound, usually there's some sort of setting they'll allow for like the volume of a voice, but once it gets too loud, something loud like a gun, it takes that wave, it sets up the complete inverted version of that wave and then adds them together. So it's not like it somehow keeps sound waves from entering in. That's not actually what happens. Actually, it lets it come in. It's just it's being added to its exact opposite wave for a completely destructive wave, if you want to call it that, which there's nothing left, so you don't hear anything. And that's how those wave canceling headphones actually work, is by adding the exact opposite wave to it. So there's a little interesting engineering application to this. All right, there's a worksheet for you to work on. It's in Schoology on adding amplitudes. You're going to be looking at pictures of two waves, and you're just going to count off the amplitude at each point in time, add it to the amplitude of the other wave at that same point of time, and then you're going to plot points and make a wave on a third graph. If when you're done it looks really messy, you probably did it right. It's not going to be a nice, pretty sine wave when you're done. It's going to look really messy when you're done. Have a good day.